All right, now it's recording. This is visible to you all?
Yes, ma'am.
Okay, so we'll begin today's class with a discussion of first order difference equations. Okay. In difference equations, some of you all might have studied this before. For those who haven't studied it before, it will be useful when we're covering the topics, the next few topics. For the others, just think of it as a refresher, okay, to help you refresh your memory. So in difference equations, we usually assume that time is a discrete variable. Okay? So time will take on only integer values. It will not take on continuous values. Okay? For example, t will be equal to 1 or 2 and so on. So we are looking at time as a discrete variable, and we usually try to look at the evolution of a particular random variable over time. Okay? What is the time path of that particular variable? What is the pattern of changes that it shows over time and so on. Okay? So we are trying to come up with a mathematical formula which will describe the evolution of a particular time series. And time series generally involves the estimation of difference equations. That's why we're covering this topic. It will be useful for the next few sections. Okay? So generally difference equations take these forms. Okay? When we take or we use the term first difference of a variable, we are basically taking the difference between the value of the variable at time t plus 1 and the value of the same variable at time t. So the choice of notation is somewhat arbitrary here. We can also write the first difference as yt minus 1. Okay, or we can write the first difference as yt minus 2 minus yt minus 1. Okay, so the choice of notation is arbitrary, but usually we are taking the first difference or the difference between the present value or current value of a variable at time t and its first lag. Okay, so that's why the term first difference is used. We use the notation delta here, okay, to denote the first difference. Now examples of difference equations are the following. Okay. This is an example of a difference equation. Now it's generally more convenient to write it this way, okay, that yt plus 1 is equal to yt plus 2. This is another example of a difference equation. Okay, and again, it's generally more convenient to write it in this way. Now, to solve a first order difference equation, okay, we try and come up with a formula which will describe or which will help us understand or be true for that variable for all time. Okay? Any formula which describes that variable for all time. So usually there are two different methods we can use. Okay? One is the iterative method, which is fairly simple. It involves successive substitutions. Okay? So we'll just go through one example. Okay? So this example says find the solution of the difference equation for delta yt is equal to 5, assuming an initial value of y naught is equal to 20. Okay? So generally to help us solve the difference equation, we assume that the series began at time 0.
Ma'am, I'm very sorry. I did not understand the examples on top. Like, I know it's only a way of showing it.
Yeah.
But like, what do we understand from that?
Okay. Let me cover a little more and then you'll understand what we mean by that particular form of the equation. Right? So here we assume, okay, that at time t equals 0, that yt takes some initial value y naught. Since t is equal to 0, the initial value of this time series is y naught, and we assume that it has a certain fixed value or deterministic value which is equal to 20. Okay? So here if we rewrite this, okay, this is already in first difference form, so if we just expand it, we get it in this form. Okay? And generally to solve the difference equation, it's helpful to shift this term to the right hand side. Okay? Now using the initial condition, we iterate forward, or we use the method of successive substitutions to arrive at a solution of the difference equation. Okay, so how do we go about it exactly? Okay, so if at t equals 0, okay, you'll find if you put t equals 0 here, you'll get y naught plus 5. On this side, you'll get y1 is equal to y naught plus 5. Okay. So this is the value of the variable at time t equals 1, okay, or a formula for the variable at time t equals 1. Now for y2, okay, just follow the same method. Since we are looking at how a variable is related to its first lag, okay, you'll find y2 depends on y1 plus 5. Okay, just follow the method of successive substitutions. So yt is here, t is equal to 1. So here you will get 2. Okay, y2 is equal to y1 plus 5. Now instead of y1, what we do is we substitute the value that we got from the previous equation. Okay. So y1 is replaced by this term y0 plus 5, and then we arrive at this. Okay. y0 plus 10 is equal to y0 plus 2 into 5. Okay. We are writing it in a form which will be easier for us to use towards the end. Okay. So following this method of successive substitutions, again you can write y3 is equal to y2. Okay, the value at its first lag plus 5. Again, instead of y2, just put this value. Okay, substitute this value. So then you get y0 plus 3 into 5. Okay, so by following this method of successive substitutions, you will be able to find that in general for any period t, okay, you can write this equation that yt is equal to y0 plus t into 5. Okay, if you look at this formula, you will find that it's true. At every iteration, what we are finding is yt at t is equal to 1 is equal to y0 plus t into 5. Okay, t here is 1. Similarly for y2, when t is equal to 2, again we find yt is equal to y0 plus t into 5. Okay, since t is equal to 2, we get 2 into 5. So this formula that we've arrived at, or this solution that we've arrived for this difference equation, it describes the value of the variable at any point of time. Okay, so it will hold good for all time. If you look at yt at any point of time, this equation will hold true. Okay, I hope you all have understood this. Is this clear to everyone?
Yes, ma'am.
Now for the second difference equation that you all saw, okay, yt plus 1 is equal, sorry, minus 0.9 yt is equal to 0. Again, we put it in a form which is more convenient to use. Okay, and here we don't have an initial condition. We are denoting the initial value as simply y0. Okay, the initial condition, we don't have a specific value for it. We are denoting it by y0. Okay. So here again we follow the method of successive substitutions. So y1 is equal to 0.9 y0. Okay. Then for y2 is equal to 0.9 y1. Instead of y1, we simply substitute this equation. Okay. So we get 0.9 square y0. Okay. Then for y3 again, it's equal to 0.9 y2. So you substitute the value of y2 from this equation. Okay. So you get y3 is equal to 0.9 cube y0. Okay. Now in general, if you look at the form of the equation that you have arrived at, it will take the form yt is equal to 0.9 t y0. Okay, so this becomes the solution of this particular difference equation.
Ma'am,
Yeah.
can we say the first one is an AP, second one is a GP?
Yes. Yeah, you can say that.
All right. And ma'am, what happens if yt plus 1 minus 0.9 yt equals to some constant? Then what will happen? Like let's say yt plus 1 minus 0.9 yt equals to like last time we had 5.
Yes,
so what if we have 5?
Yeah, we are coming to that now. Okay, the next part discusses that. Okay, so we'll discuss that part now. So now for any difference equation, so far you'll have been able to follow it. Okay, the two solutions are slightly different. I hope you'll have been able to follow it. Now the general method, if you're given a general representation of a difference equation, okay, let it take this form, yt plus 1 plus ayt is equal to c, okay, where a and c are assumed to be some constants. Now the general solution for this difference equation, which is of this form, okay, it can be broken up into two parts. One is called a particular solution or particular integral. The other is called a complementary function, okay, and they're denoted by yp and yc. Now the particular solution, it basically gives an equilibrium value of the particular time series that we're looking at. Okay? So you can think of it as some sort of an equilibrium value which the series will take over time, okay? Some sort of an intertemporal equilibrium. Now the complementary function will look at the deviations or fluctuations around this equilibrium. Okay? So it will basically describe the fluctuations around that equilibrium. So the general solution will be the sum of these two components, the particular solution or that equilibrium value and the complementary function or the fluctuations around that equilibrium value. Okay, now to solve this general difference equation, where you have a constant here. Okay. So first we'll take up this aspect or this part of the solution, the complementary function. Okay. Now to arrive at the complementary function, we usually put all the yt terms together. Okay. So yt and its lags will be put together and the equation will be equated to 0. Okay. And then we begin solving. So generally for the complementary function,
Ma'am, why would I have taken 0 and not C?
because for the next part we are using this entire equation where we'll be using C.
So we are trying to find the value of C.
Yeah, okay, just be a little patient. Let me come to the next part and you'll understand how we are proceeding. Okay. You'll have studied difference equations before?
No, ma'am.
No, ma'am.
I mean, we've just talked about it, but we've never gone into the theory.
Yeah.
Okay, but so far you'll have been able to follow it? So
Ma'am,
far,
can you
what
repeat? Can you
Yes.
repeat about particular and complementary function?
Yeah, okay. So the particular solution or particular integral, it's basically an equilibrium value. So in every period, you can think that there'll be some constant value or equilibrium value which yt can assume. Okay. So this particular solution will give that equilibrium value, okay, which will describe some constant value towards which yt is moving. You can think of it that way. Okay. The time series yt is trying to achieve that particular equilibrium value. So yp or this particular solution gives you that equilibrium value of the time series. Okay. And the complementary function, it basically describes the fluctuations around that equilibrium. Okay. So just if you're trying to imagine it graphically, just think on a graph, okay, there's a horizontal straight line which is parallel to the x-axis. Okay. So that you can think of as being your equilibrium value. Okay. It is at some constant. Now, if you think of a sinusoidal wave or curve, okay, which is moving up and down around that equilibrium value or around that horizontal line, you can think of that as being the complementary function. Okay. So what we say is that for any, the solution to any difference equation, it's made up of these two parts. There'll be an equilibrium value and there'll be the fluctuations around that equilibrium value. Now, in order to find this part of the solution, the general solution for a difference equation, we take all the yt terms, okay, the terms that are related to that particular time series, we take them together, bring it to one side, left hand side, and equate that to 0. Okay, and then we begin solving from there. Now, just assume, okay, this is the method of solving. This is how we solve it. So, we are going to assume that yt assumes some value abt at time t. Okay, and this is some constant value. You can think of it that way. B is a constant. Okay, A is also some constant, and t denotes time. Okay, and we are also assuming that abt, this whole product, is not equal to 0. Okay. Now, since we are assuming that yt takes this equilibrium value at time t, okay, at time t plus 1 also it will take that value, but here you just need to change the time subscript. Okay, so at time t plus 1, yt plus 1 will take the value abt plus 1, okay, since this part denotes time. So then we just substitute these two values in this equation. Okay, in equation 2, we just substitute these two values that we have assumed for yt and yt plus 1. Okay, so for yt plus 1, we put it down as abt plus 1. For yt, we put abt. Okay, so we get minus abt is equal to 0. Now, since abt is common, we bring that out. Okay.
And ma'am, it should be minus a in the bracket.
Sorry?
In this bracket, it should be b minus a, right? Not plus.
Just a minute. I think here I made a mistake. Okay, since this should be plus. If you remember, we brought these terms to one side. They're already on one side, and the sign here is plus. Okay, so this should also be plus. So the next part is correct. Okay, so just if you're noting it down, just make that correction. This will be a plus here. Okay. So here you get abt plus 1 plus a into capital ABT is equal to 0. Okay. Now, since ABT is common, okay, we bring that out, and here in the brackets you get B plus A is equal to 0. This is a mistake. Okay. This should be plus here. Okay. So now if you solve further, you will find that B is equal to minus A. Okay. So we found one part of the solution here, that B is equal to minus A. So for the complementary function, okay, just remember that we are assuming that yt takes the value abt. Okay. So here the value of yt at time t, again instead of abt, we'll just put the value of b that we found, which is minus a, okay, raised to the power t. So this becomes our complementary function. Okay, the value of our complementary function is equal to capital A into minus a to the power t. Okay, so we got one part of our solution. Just remember that you just bring all the yt terms to one side, set it equal to 0, and then go about solving by assuming that yt assumes a value abt at time t, and so on. Okay. So far, is it clear to you all? Any doubts about what we have discussed so far?
No, ma'am.
Okay.
So, ma'am, as the time increases, the value of yc will tend to 0.
yc, okay, yeah, that's good. Okay, that you arrived at that conclusion. Yeah, that's something that we'll be reaching a little later. Okay, now we'll come to the particular solution. Now for the particular solution, just set yt is equal to k, some constant. Okay, again you're assuming this. We proceed by trial and error here. Okay, so if this method doesn't work, some other method can be used. But since it's a simple difference equation that I've used here, okay, this method will work. So we set yt is equal to some constant at time t. Okay. Now since it is some constant, even in yt plus 1, okay, at time t plus 1 also yt will assume that same value of that constant. Okay. So now just use this and substitute it in the particular difference equation that we had. Okay. So this was the same difference equation. Here we are using the whole equation. Okay, we are not setting it equal to 0. So now yt at time t is equal to that constant k. At time t plus 1 also it's equal to that constant. Okay, so we just substitute and we find that k is equal to c by 1 plus a. Okay? So this gives us a particular solution or the equilibrium value. Now here we are assuming that a is not equal to minus 1. Okay? Because if a is equal to minus 1, the solution will not be defined. Okay? So we are making this assumption that a is not equal to minus 1. So this gives us a particular solution. Okay? So if you notice in both cases, we are making certain assumptions about the value that yt takes at time t and t plus 1, and then we are proceeding. Okay? So this gives us a general solution, which will be the sum of the particular solution and the complementary function. Okay, so this is the complementary function, this is the particular solution. And this is for the case where a is not equal to minus 1.
Ma'am, could you just go to the previous page for a second?
Yeah.
Could you just give me 1 minute a copy? That's fine with you.
Yeah. I hope this is clear so far. Have you all understood so far?
Yes, ma'am.
Ma'am, these derivations will be asked in the exam.
Do you all have physical exams or do you all have exams online?
Ma'am,
Online,
most,
ma'am.
yeah,
It's
online only.
Okay. Then you can be sure that you won't be asked this.
So these derivations are just for our proving to us, not for.
Not just proving to y'all, so that you'll understand the subsequent portions. Okay, otherwise you'll feel that it's just a bunch of derivations, they won't make sense to you.
Okay, ma'am.
Just let me know once you've finished copying, all right?
Ma'am, just I know this might sound silly, but ma'am, here we've assumed that yt is a b to the power t. What if we would assume it is in a certain different functional form? Then we would move into a different set of problems.
Yeah, but this is the method which is generally used, okay, to solve difference equations.
So
This is
ma'am,
the form of the general solution.
my question would be why? Like, is there any particular reason why we're going ahead with this, or we're just doing what has been done for many years?
Again, I'll ask you to be a little patient. Okay? You'll understand probably by the time we reach the end of the class. Okay, so you'll have to be very patient today.
Right, ma'am.
Ma'am, also one more question. So I understood the mathematics of it, that
Yes.
we first found the complementary function and then we go on to the particular solution. But I don't understand the relationship between the two, or why we are doing these things.
Yeah. Again, you'll have to just wait till the end of the class. Okay, so that will hopefully help you understand what we're trying to get at.
Okay, ma'am.
Just think that it's a movie where like everything is building up to some grand conclusion. Okay? So have you finished copying?
Yes, ma'am.
Okay.
Done.
Now, if you look at the form of this general solution, okay, you'll find that it is not determinate or it doesn't have a fixed value because of this arbitrary constant. Okay, we haven't given any particular value to A, okay, or we haven't said it's an initial value or anything like that. Okay, so it's basically an arbitrary constant. It can assume any value. Now, to get rid of this A, okay, which is arbitrary, we usually use an initial condition yt is equal to y naught when t is equal to 0. Okay, so at time 0, we assume that yt will assume a particular value y naught, which is called the initial condition, and then we proceed from there. Okay, when you are actually given a problem, y naught will have some particular value, okay, numerical value, and then you will proceed from there. Okay. So let t equal 0 in equation 4. Okay, so if t equals 0, you're just left with y naught Okay? Even here you will be assuming that t equals 0. So you are left with y naught is equal to a, because any term raised to the power 0 is 1. Okay? So y naught is equal to a plus c by 1 plus a. Okay? Now using this equation we can solve for a. Okay? So a is equal to this term. So now if you substitute this in
Excuse me, ma'am.
equation 4, yes?
Ma'am, I had a doubt. While finding out the particular solution, we kept the value of yt and yt plus 1 both to be k.
Yes.
We assumed the value to be k for yt and yt plus 1.
Yeah.
So does that mean that we are assuming that the time series is not changing from yt to yt plus 1?
If you remember what the particular solution is, it's basically an equilibrium value. Okay, so we are assuming that the equilibrium value for this time series yt is k. Okay, so in every period that equilibrium value will remain the same. And k is appearing in this equation in this form. We solved for k, so k is equal to this.
No, ma'am, I understood that. What I'm trying to ask it, so basically we are modeling autoregressive processes, right? That's
Yes.
why we can make these assumptions, right? So we are assuming that there is a particular mean or an equilibrium point of the
correct.
series.
Yes.
But if we weren't modeling autoregressive processes, for example, we are modeling moving averages, then we couldn't do this, right?
That we will discuss when we're discussing moving averages. Hopefully tomorrow we'll do that. Okay? So I don't know how many of you all are familiar with moving averages. So we'll cover that tomorrow. Okay,
Okay, thank you.
So if you're looking at the definite version or the determinate version of this general solution, okay, it will take this form. You can substitute the value of a from equation 5 into equation 4. Okay? So we find that this is the form of the general solution, which is a determinate solution. It has a certain fixed value because we've used the initial condition y naught here, okay, to arrive at the solution. So this gives us the general solution and the definite version of the general solution. Okay, now we'll try and look at problems and see if you're able to solve some problems using this same method of breaking down the solution into a particular solution and a complementary function. Okay, just try
Ma'am,
and
could you just
remember.
scroll up for a second? I'm so sorry.
Just try and remember what was discussed. Okay, if you made notes, you'll be able to refer to your notes. If you haven't, just try and remember what was discussed so far, and you'll be able to solve the next few problems. Again, please let me know once you finish copying.
Ma'am, if you can scroll down.
See, instead of copying, just think about what you understood and then proceed from there. If you want to verify whether your solution is correct, what you can do is, for the particular solution, you can just substitute the value of k on the left hand side, see if you're getting the answer on the right hand side. Okay? If you're getting that same constant C, that's for the particular solution. Then for the whole equation, if your general solution is correct, you can just substitute and see at t is equal to 0. Okay? What is happening to your equation? Are you getting y0 or y0 here on the right hand side? Have you all finished copying?
Yes, I'm done.
Yes, ma'am.
Okay. We'll just try and solve one or two problems. Oh, sorry, it's the same one. Okay, now just don't look at the solution part of it. Okay, you can already see the first part, the complementary function part. Okay, try and do it without looking. For the particular solution, you can do it referring to your notes or from memory. Okay, try and solve this first order difference equation. Okay, just let me know once you all finish solving the equation. Has anybody finished?
I'm just a few minutes. Just give us 1 minute, please.
Yeah.
Ma'am, you won't be asking difference equations in the exam, right? Like asking us to give a solution to a difference equation.
I might, yeah, I just realized I might be able to give you all this kind of a problem, so I might.
So
It'll
if
be
you
simple.
do, then do we need to solve the whole thing, or can we just like replace the coefficients? For example, in this question, right, we can just replace the coefficients. Like we can replace a with -5 and we can replace c with 1, and we'll get the answer. So then,
You're
so
replacing capital A with -5, is it?
no, the small a with -5.
Oh, okay, okay. Yeah, if that method helps you arrive at the solution, yeah.
Ma'am, I think
But
the
I
answer.
think the problem, the previous one had a plus sign, right? In the
Yeah, that's why we are doing a
yeah.
-5, right?
Okay.
Ma'am, I think the answer might be 19 by 12 multiplied by 5 to the power t plus 1 by 6.
Did you use the initial condition?
So, ma'am, initial I used, so ma'am, I started with yt plus 1 minus 5 yt equals to 0. And
Yeah.
then and from there I got that yt equals to some constant to the power 5 to the power t.
Okay. Yeah.
Okay. I think that it's 1 by 4, not. So, okay, ma'am, I think the answer is 3 by 4. 1 by 4.
Okay, just work on the
Yes,
last
ma'am.
part. Your
Minus 1
complementary
by
Ma'am, is
4.
function
it
is
2
correct.
into 5 raised to the power t minus 1 by 4?
I'll just give you another minute. Okay, some of you seem to have got it. Okay, just your complementary function is correct. Just work on the particular solution part and the A part. Okay. For the A part, you have to just assume that t is equal to 0. Substitute that number 0. Okay, wherever you find t and then solve.
Oh. Is it yt is equal to 2 into 5 to the power of t plus 2?
Okay, I'm showing you the solution. Yeah. So this is the definite solution. I've given you the general solution. Then once you solve for A, you'll find that this is the definite solution. I hope all of you have been able to get this answer.
Yes, ma'am.
Yes, ma'am.
Okay. Yeah, I'll just show you all quickly for the particular solution. Okay, just assume again that yt is equal to some constant k at time t and t plus 1. Then use that entire difference equation to solve for k. Okay. Then once you've done that, just let time t is equal to 0, substitute that over here, and then find out the value of a, and then just substitute in your general solution again. So you get the definite solution. Right, we'll quickly do one more. I think it will get easier for you all. Okay, please don't look at the solution right now. Yeah. Okay, you all can solve this one. Yt plus 1 is equal, plus 3 yt is equal to 4. The initial condition is y naught is equal to 4. Okay, just solve this quickly, just so that you all get the hang of it. Once you all finish, just let me know.
Ma'am, I may be wrong, but I think the answer might be 3 multiplied by minus 3 to the power t plus 1.
Okay. Anybody else got the same answer?
Yes, ma'am.
Yes, ma'am, I also got the same answer.
We
You all can verify the solution by yourselves, all right? Just substitute the particular solution value in the equation, difference equation itself. If you get the answer, then your particular solution is correct. Otherwise, if you take yt plus 1 is equal to minus 3 yt plus 4, okay, and then look at the value of y at time t is equal to 0. Okay, if you are able to get the same answer, then your solution will be correct. So you can verify it yourself. Yeah, I'll just show you the solution. You all can see this, right? So this is the complementary function part. Okay, then the particular solution is equal to 1. All right, then you can find a by assuming let t is equal to 0, a is equal to 3. So this is your definite solution. Yeah, I hope all of you got this answer. You all are comfortable with this right now, no? Okay, can we move on? Are you all copying the answer or shall I move on?
can move on.
Yeah. Now somebody was talking about this a little earlier. Okay, now the dynamic stability of equilibrium, okay, depends on this term ABT. Basically this term that you got from your solutions. Okay. Now as t tends to infinity, or as the sample size grows larger and larger, as you have more number of observations, okay, what will happen to BT? Okay, b raised to the power t. Okay, we'll just look at it, what happens exactly to this variable b raised to the power t. Okay. Now if b is a positive constant, okay, then the time path of this variable b raised to the power t itself, it will be non-oscillatory. So basically the time series that you're seeing, okay, it will not oscillate, or you'll not see fluctuations, up and down movements in it, okay, as it's moving towards equilibrium. Now if b
Is it the assumption that we are taking, or is it?
No, I'll show you with some examples. Okay, this is true whatever number you take, so it's not based on assumptions. Okay, so I'll show you some probably graphs, and then you'll be able to understand better. Okay. Now, if b is positive, you'll see that this time series, it will have a non-oscillatory path, so there'll be no fluctuations. It will move in a steady way towards equilibrium, okay, without any fluctuations. Now, if b is negative, okay, then you will have oscillatory movements in the time series as it's moving towards equilibrium. Okay. So you will see up and down movements of fluctuations in the time series as it's moving towards equilibrium. Okay. This is as the sample size is growing larger, or as t tends to infinity, okay, as the number of observations are increasing. Now somebody had mentioned this, okay, so your intuition was correct. I think the top part of this is not visible. Okay. But if you take the absolute value of b, okay, if the absolute value of b is greater than 1, you will find that the time series is divergent. It will not move towards the equilibrium value. Okay. It will diverge away from equilibrium, the equilibrium value as time progresses. Instead, if the absolute value of b is less than 1, then the time series will be convergent. Okay. So here you will find that the time series will be converging towards equilibrium will not move away from equilibrium as time progresses. Okay? So just keep these two things in mind. If B is positive, okay, then you will see non-oscillatory movements. If B is negative, you will see oscillatory movements, okay, or there will be fluctuations. Again, if the absolute value of B is greater than 1, the series will diverge from equilibrium. If the absolute value is less than 1, it will converge towards equilibrium. Okay. Now, what role does A play? Okay, all this is from the complementary function part. Okay. So, the role of A is that it produces a scale effect. So, whatever is happening to B, okay, B raised to the power T, A's role is either to magnify it or to dampen that effect. Okay. So it will produce a scale effect. Now the sign of A also affects the shape of the time path that a time series takes. Okay. So for example, if A is positive, okay, then you will find that the time path will have a certain appearance. If the same A value is negative, okay, you will see a mirror image of the time path if the value of A was positive. Okay, I'll show this to y'all so y'all will understand it better. But basically it affects the shape of the time path in the sense, are you seeing it on the negative axis or the positive axis? Okay. So A will produce a scale effect. It will either magnify the impact of B raised to the power T or it will subdue it or dampen it. Okay. Then when you're looking at the convergence to equilibrium itself, if you look at the solution, this is the entire solution. This is the complementary function. This is the particular solution. Okay, I've written it in the general form. Now this solution will be convergent for a particular time series only if the absolute value of B is less than 1. This is something that was written above. Okay.
So ma'am, please scroll up a bit about the convergent and divergent.
See, nothing, I think I didn't photograph this part. So for divergent, you'll just put mod B or absolute value of B is greater than 1. Okay, that part is not visible in the photo anyway.
Thank you.
Okay, now I hope you all have understood this. We'll take a look at it with some examples. Okay. Can I close this? Can I close this so that I can show you all
Yes,
that
ma'am.
example? Yeah. Okay. Now, if you look at the value of B, okay, this is for different time periods. What happens if B is greater than 1? Okay, and if the absolute value of B is also greater than 1. Okay, and we have taken certain examples. This is time. Okay, here what you see here, what I'm highlighting, this is time t is equal to 0, 1, 2, 3, and 4. Okay, so this first one, I'll just highlight it in yellow. It's talking about the time period, okay, the specific time period. And just remember that we're looking at time as a discrete variable. So yt or the time series, it will assume a specific value at time t equals 0. Then the value will only change when time changes to t is equal to 1. Okay, in between nothing happens. So here for the case where b is greater than 1, okay, and the absolute value of b is also greater than 1. Let's take the example of 2. Okay, here if 2 is raised to the power t, b is assuming the value b is equal to 2. Okay, so at different time periods, what value is this term going to assume? B raised to the power t. Okay, at time 0.
Ma'am, could you zoom in by one level? I'm so sorry.
Yeah.
Thank you, ma'am.
So, just a minute. Yeah. So 2 raised to the power 0 is 1, 2 raised to the power 1 is 2, and so on. Okay, that's how I've arrived at these values. Okay, we are taking b is equal to 2 and then seeing what is the value of bt at in these different time periods. Okay, now if I plot this, okay, what you will see is, since the absolute value of b is greater than 1, okay, you'll see it moving upwards, okay, the graph. Now, since we are looking at time as a discrete variable, this should actually be in the form of steps, okay. So at time t is equal to 0, it's equal to 1, okay. Then at time t is equal to 1, it will assume the value of 2. So imagine it as a step function, okay, and not as this smooth curve here that you're seeing. Now, since the value of b is greater than 1, okay, or it is positive, you do not see any oscillations. That's what I was talking about earlier. So for positive values of b, you will not see oscillations. And since the absolute value of b is greater than 1, you see a divergence from equilibrium. Okay, here we don't know what that equilibrium value is, but you can see that it is moving further and further away. Okay, so you cannot see that it will converge to some sort of an equilibrium. Now, similarly, if you take, in the case of b is equal to 1, you will see a different result. Okay? So here, you will find the same value for all time periods. Okay? That is natural. You can understand it by yourself. So I will not go into it. Now, if b lies between 0 and 1. Okay? So the value is less than 1. It lies between 0 and 1. And the absolute value of b is less than 1. Here you will see some sort of a convergence. Just remember, absolute value of b is less than 1. So you should see it moving towards the x-axis. There will be some sort of a convergence. Okay, here we have taken this example where b is equal to half. Okay. Okay, so you can see that it is converging in some sense. Okay, we don't know again what the equilibrium value is, but you can guess that it will be converging. Okay, again, since b is positive, you will find that there are no oscillations, okay, or there are no fluctuations here. Now again, for the next case, b is equal to 0. I will not go into it. Okay, so this will just be the horizontal line on the x-axis. Now, so for this part, okay, you can look at it over here. So b lies between -1 and +1. Okay? And here b is, the absolute value of b is less than 1. Okay? So again, we are expecting some convergence to take place. You're assuming here that b is equal to -1. Okay? Sorry, minus half here. Okay? So what do we see? Okay, again, imagine it as a step function, but here you see some sort of a convergence again. Okay, so it's moving closer and closer to the x-axis. You can imagine that some sort of convergence is taking place. But since the value of b is negative here, okay, so we see oscillations here or fluctuations, up and down movements. Okay, now the same thing. Again, if b is equal to -1, okay, you will find that for t in this term b raised to the power t, when t is an even number, you will find that b is equal to 1, okay, or it will have a positive value. When b is an odd number, sorry, when t is an odd number, okay, b will have a, sorry, this term will have a negative value. Okay, so for odd values of t, you will have negative values of the b raised to the power t term, and for even values of t, you will have positive values of this term b raised to the power t. Okay. Now for this last one, b is less than -1. Okay, so here again it is negative. So what we are expecting is oscillations or fluctuations. Okay. And since b is, the absolute value of b is greater than 1, we are expecting that this series will be divergent. Okay, so let's see what happens here. Here we are assuming that b is equal to -2. Okay. Okay, so here you can see that divergence. Okay, that's clear from the graph. Again, you can see oscillations. Okay, because B is negative here. Okay, so B plays an important role in determining whether convergence or divergence will take place. Again, you will see that as time progresses, this is what somebody was mentioning. Okay, if the absolute value of B is greater than 1, okay, you will find that that whole term will keep getting magnified, or it will keep growing larger and larger. Okay? Instead, if the absolute value of B is less than 1, okay, for example, in this case, you will find that that whole term a b raised to the power t, that will keep getting smaller and smaller, and eventually as t tends to infinity, you are expecting that b raised to the power t will tend to 0. Okay, so here, just to show you the scale effect, okay, we'll just take this where b is equal to 2. Okay, so here just think that a is equal to 5. Okay, so we are trying to produce the scale effect or see the scale effect here. Okay. So let's just look at this. So if you look at this orange line, this is your a into b to the power t. Okay. And this blue line here is simply b to the power t. Okay, so you can just see that a has only scaled up this same line, okay, by 5 times. So it produces this scale effect. Now what if instead of a being positive, a was negative? Okay. Here you will see the mirror effect along with the scale effect. Okay. Okay, so I'll just plot only these two, A, B, T. Okay. So this one is for positive values of A. Okay. And you can see this where A is negative, we assumed A is equal to -5. It just produces a mirror image of what we were seeing earlier. Okay. So here you can see the mirror effect as well as the scale effect, okay, that A produces because A is negative. Here, since A is positive, you only see the scale effect. Okay, so I hope this was clear to all of you how the value of B plays an important role, and also how the value of A plays a role in convergence. Okay. B is more important, of course. A only produces the scale effect or the mirror effect or both. Is this clear to all of you? So far, whatever was discussed, was it clear?
Yes, ma'am. Regarding A and B, yes.
Yeah. Okay, so I'll just let you take a look at this part again. Okay, if B is positive, you'll see the time path of Bt will be non-oscillatory. If B is negative, the time path of this term will be oscillatory. Okay. And the other part was about the absolute value of B. If the absolute value of B is greater than 1, you will find that the time path of that term is divergent. If the absolute value is less than 1, the time path will be convergent. So in sum, the whole time path for this difference equation, okay, will be convergent only if and only if the absolute value of B is less than 1. Okay, this is an important thing to remember. Okay, now we'll continue with the next part where we are actually dealing with autoregressive processes. Okay, since somebody mentioned that already, some of you are probably aware of what this means, and I think Kamaya sir also must have discussed in the first class. Okay, so in the first part of the course, what we are dealing with are univariate processes. Okay, so we are looking at a single variable, for example, the time series yt, and how it's related to its own past values or the past values of the errors and so on. Okay. So here, since we are using only a single variable for analysis, it's called a univariate process. Okay, where they're studying the evolution of a single process, how it's evolved over time. Now, what we'll be studying first are known as autoregressive processes. Okay? Why is it called autoregressive? As the name indicates, you're looking at how yt, okay, the value of a particular variable at time t, how is it related to its past values or its lags? Could also be related to its leads and so on. Okay? But generally, since we look at how the past determines the present, they are known as autoregressive processes. Okay, now in this equation over here, okay, what you're seeing is a pth order autoregressive process. Okay, since we've taken lags up to time p, okay, so here you have yt minus 1, yt minus 2 up to yt minus p. Okay, so we've used p lags, so that's why this is called a pth order autoregressive process. Okay, but first, just to understand these processes, we'll look at first order autoregressive processes, and then we'll be able to deal with higher order autoregressive processes. Okay. Again, as the name indicates, you'll find that the first order autoregressive process is a process where you're relating the current value of a variable y at time t to its first lag, okay, y at time t minus 1. So since you're relating it to its first lag, it's called a first order autoregressive process, or also a AR1 process. Okay. If you have AR2, then you're relating yt at time t to its past two lags, okay, or the previous two lags, first two lags basically. Similarly, for a ARP process, you're relating yt to its p lags, okay, to its past values up to lag p. So first we'll look at first order autoregressive processes, or AR1 processes as they are known. Okay. Again, you'll be solving this. If you look at it, it's basically a difference equation. But how is it different from what we dealt with so far? It's different because of this term here, okay, which is the error term. Here again, we'll be making certain assumptions about this error term, that it is a white noise process. Okay. So if it's a white noise process, basically it means that we're assuming that expectation ET is equal to 0. Then variance of ET is some constant. Okay. It is finite and some constant. Then covariance between ET and its lags, ET and ET minus S, is equal to 0. Okay. So there's no autocorrelation in the error terms. Okay. So these are certain assumptions we'll be making about the error terms in this AR1 process. Now to solve this, okay, again, just to come back to the difference between this and what we did earlier, okay, this is the deterministic part of this process. Okay, if you look at this, this is A0 is some constant, A1 is also some constant. Okay, but the stochastic part of the process comes in because of the error term. Okay, so this is known as a stochastic difference equation and not a deterministic difference equation. Okay, because of the presence of the error term. Now the solution, the way we find the solution will be somewhat similar. Okay, so we'll go about it. That's why I took you through solving difference equations. Okay, so again, we solve or find a solution by the process of iteration. Okay, given y0 or some initial condition for this time series yt, okay, we begin solving assuming that there's some initial condition which is known. The value of y0 is known. Okay. So here we write this equation again. I've written equation 1 again. Now instead of t, okay, what you can do is put 1 here. Okay, instead of t, put 1. So y1 is equal to a0 plus a1 y0. Okay, since 1 minus 1 is 0, you will get a1 y0 plus e1. Then y2 is equal to, the same way, keep substituting. Okay, so y2 is equal to a0 plus a1 y1 plus e2. So you're solving in a recursive fashion or by substituting successively. Okay. Now instead of y1, we'll put in equation 2. Okay, substitute y1 with equation 2. So you get this form of the equation. Simplify it further. This is what you get. Okay, once you open up the brackets. So we get equation 3 this way. Then again y3 is equal to a0 plus a1 y2. Okay, you're relating yt at time t to its lag, first lag. Okay, so you get y3 is equal to a0 plus a1 y2 plus e3. Okay. Again, instead of y2, we just plug in equation 3. Okay, substitute equation 3. Okay, you get this form of the equation. Okay. And then this. So if you keep repeating this for all time, okay, as t assumes positive values, if you keep doing this over and over again, okay, repeated iteration will result in this. Okay, this will be the general solution for this equation, okay, this stochastic difference equation. So if you look at the form, okay, if you look at y3, you'll be able to understand why it's taking this particular form. Okay, so yt will be equal to this term. Okay, if you look at the first part here, okay, you're just summing up all these components, so that's why you get this term. Similarly here, when y is equal, y at time t is equal to 3, okay, y3 is equal to a1 t. Since t is equal to 3, again you put the same thing here. Okay, so that's why you get this form of the solution, a1 t y0. Then similarly, you're just summing up these error terms, so that's why you get this term. Okay. So this is the form that the general solution takes. Okay. So now equation 4 is a solution to equation 1. That is very clear. Okay. So far, are you all with me? Are you all following? Any doubt so far? Anything that you did not understand?
No, ma'am.
Okay. Now that one, what we saw earlier was a little easy to solve because we assumed that there was an initial condition, why not? Okay. But what if we don't have an initial condition? So why not was not given. Okay. Then since we don't have a fixed value for why not, okay, no matter how far back in time we go, or you can find the solution also by, in that case, if you look at it, we were iterating forward. Okay, we are going from y1 to y2 to y3 and so on. Even if you went backwards, okay, if you went from y0, how is it related to the previous value and so on, you would have reached the same solution basically. Okay. But in this case, if you do not have an initial condition, okay, then what you will find is that no matter how far back you go or how many times you try to iterate forward, okay, you will not be able to reach a conclusion or a solution. Okay. So now suppose we continue to iterate backward by substituting. Okay. For y0, if we had substituted further, okay, so y0 is equal to a0 plus a1 y minus 1. Okay, since you're assuming t is equal to 0, so you get y minus 1 plus e0. Okay, for y0 in equation 4. Now, if you substitute, okay, for y minus 1 in equation 4, if you substitute for y0, then you will get this value. Okay, instead of y0, we are just putting in this term in equation 4 that we saw on the previous page. Okay, so once you substitute this value, okay, if you simplify it, this is what you will get. Yeah, I'll just give you a minute to take a look at it. Okay, once you multiply this, this becomes a1 t a0. Okay, so this just becomes plus 1 here. Okay, so this is subsumed here or incorporated here. So you get this term where the index changes to t. Okay, the same thing happens over here. And this is just a1 raised to the power t plus 1 y1, y minus 1. Okay. Now, if we keep doing this further, okay, we go back another m periods. This is what we'll get. Okay, yt is equal to a naught, this whole term. Okay, I won't read it out. You're just adding m here because you're moving back m periods in time. Okay. Okay. Is equation 6 clear to you all? Have you all understood it?
Ma'am, how we got t plus n?
T plus m. Okay, we are assuming that you're repeating this process. You're going back repeatedly another m periods. Okay, that's why you get here minus m. Okay, so you're doing the same process of substitution. So for y minus 1, again you'll write out the equation. So you'll get a naught plus a1 y minus 2 and so on. Okay, plus e minus 1. Okay. Like that you'll keep moving backwards in time another m periods. This is what you're doing. Later on, once the class is over, okay, once I share the notes, probably by Monday you'll get the notes. You can try it on your own. Okay. But if you go back another m periods, if you keep substituting the way we did for the previous equations, when you took y1, y2 and y3 and so on, okay, at each stage you were substituting, right? So if you keep repeating that process, finally you'll end up with this equation. Okay, but basically if you look at this, you'll be able to understand. If you have another m terms here, okay, so then this whole thing will increase by m. Earlier in this equation, it increased by 1, so we ended up with t. Okay, you had plus 1 here, so we ended up with t. Here, if you add another m terms, you'll just get t plus m. The same logic can be applied here. You'll get another m terms here for the errors, so you'll get t plus m. Okay, the same way over here. You add another m terms and you're going back m times. Okay, so that's why it's y minus m minus 1. Okay, it might be clearer once I share the notes, but just think that you're going back another m lags or m periods in time. So you end up with this solution of the equation. Okay, but is it really a solution? Okay. Now, if mod a or the absolute value of a is less than 1, okay, then as m tends to infinity, as we keep increasing the number of lags or as we add more and more observations to our sample, okay, this term a to the power t plus m plus 1, which comes here, that will basically tend to 0. Okay, that's something that you saw from the Excel sheet also. Okay, that if you raise some number to a very high power, okay, and if that number, the absolute value of the number is less than 1, then you'll find that it slowly begins to shrink in value and it gradually will approach the value of 0. Okay, so this term will basically vanish. Okay, as you go back in time, as m tends to infinity or your sample size becomes very large, this term will vanish, okay, because this term will tend to 0 or converge to 0. Okay, similarly, if you look at this, okay, this was more clear in the previous photo, okay, but this term basically, it is a naught into this whole term in brackets. Okay. So this is nothing but an infinite series which will converge to this value. Okay. Because you're assuming that time tends to infinity. Okay. So here, as you go back in time further and further, this infinite series will converge to this value. Okay. So these two terms are taken care of here. Okay. This converges to this value and this term will vanish. Okay. So now in order to find our solution, we assume that the absolute value of a is less than 1. So we can write this equation as this. Okay. Also, we are assuming that t tends to infinity or we are taking a very high number of lags. Okay. So yt will be equal to this term, which is what this infinite series converges to, and it will be equal to this summation of the error terms. Okay. So far, are you all with me? Are you all following? Have you all understood?
Yes, ma'am.
Okay. Now equation 7, okay, is a solution to the first difference equation that we saw, okay, which is your yt. You go back to this page. Yt is equal to a naught plus a1 yt minus 1 plus et. Okay, so it's a solution to this equation. Now, if you want to confirm whether it's a solution, you just need to substitute and check whether you're getting the same solution. Okay. For example, if yt is equal to y naught, are you able to get this solution? Okay, that's what I'm suggesting. So here, equation 7 is a solution to that first equation that we saw. Okay, but if you notice, equation 7 is not a unique solution. Okay. Now, for any arbitrary value of a solution to here equation 1, okay, this should be equation 1, is given by this term. Now, why am I saying this? Here you'll recall how we wrote the solutions for different equations. That a b raised to the power t term was coming in there. Okay, so this is taking a similar form. So for any arbitrary value of a, the solution to equation 1 will be given by this equation, equation 8. Okay, now let's verify whether this can be the solution. Okay, for any arbitrary value of a. If you substitute this equation into equation 1, okay, so yt is equal to this. Okay. Now at time t is equal to 0, okay, you're just substituting this in equation 1. Okay. Earlier you had yt is equal to a naught plus a1 yt minus 1 plus et. Okay, that was your equation. Now we are just substituting this equation 8 here. Okay. And at time t is equal to 0, okay, what happens? So here at time t is equal to 0, you will find that you get this form of the equation. Okay. Instead of y0, you will just put this. Okay. Since you're taking it back one lag, okay, this is what you're doing over here. So you'll get this. Now the two sides are identical. Okay, so 8 is a solution for 1. If you simplify this further, okay, what you will find is what you found on the right hand side of equation 1. Okay. I'll just give you a minute so that you can verify whether it's actually a solution to equation 1. Okay, so if you've been able to follow so far, what you'll notice is you're getting the same solution here. Okay, this term, once you substitute this in equation 1, you'll just, if you simplify this further, you'll just end up with this or with equation 8. Okay. So since the two sides are identical, we say that 8 is a solution for 1. Once I share the notes, you'll be able to do it for yourself and check. Okay. Don't try and copy this part. Okay. Just listen to me now. Now given equation 8, Okay, suppose we are given an initial condition concerning the value of y in some arbitrary time period t0. Okay, so since you want to solve it, it's not in a determinate form or definite form. Okay, and we want to find out this solution in a definite form. So since a is some arbitrary constant, okay, we are going to assume that there is a specific value which y takes in time period t is equal to 0. Okay. Since 8 is true for all periods, then when t is equal to 0, you will get y 0 is equal to this. Okay. If you just substitute in equation 8 and wherever t is appearing, if you just put 0, okay, you will end up with this equation. I'll just show you the previous equation again of this. So this was equation 8. Okay, so wherever t is appearing, if you put 0 over there, okay, what you will end up with is the next equation that we are discussing. Sorry, I think I already showed you all this. Yeah. Right, so when you assume t is equal to 0, you end up with this equation. So you can use this to solve for a now. Okay. So you will find out the value of a. So now since you're finding out the value of a in terms of some specific constants which are given to you. Okay. So equation 9 is a value of a that renders equation 8 a solution to the first difference equation that you came across given this initial condition, why not? Okay. So because we are finding out the value of a using the initial condition, we are able to find a specific or definite solution to the difference equation. Okay. Now if you substitute equation 9 in equation 8, okay, for a if we replace a with this term, then you get the entire expression or the definite solution of the difference equation or the first order autoregressive process. Okay, so if you simplify this further, you will get this. I'll share the notes so it will be easier for you all to understand. Okay. Any doubts or questions so far? You all might not have followed the last part of the derivation, so I'll share the notes. Once you look at the notes, you'll be able to understand it clearly. Okay, but other than that, any doubts?
No, ma'am.
No. Okay. Now, if you look at this, this has a similar form to the solutions for the difference equations that we were using earlier, okay, or that we solved for earlier. Now, why is this important? Why do we need to bring it into this form, and then why do we impose certain restrictions on the coefficients, okay, for this particular AR1 process?
Just a little request, ma'am. Can we continue this tomorrow? I think it's a lot to take in for today.
Okay, fine. All right, I'll just show you all one thing. So then that might help you understand a little better. Okay. Right, just look at this form of the solution. Okay, or even if you look at this form of the solution, it will be helpful. Okay, just keep in mind here that A1 is raised to the power t. Okay? And here this is attached to the initial condition. Okay? Similarly, a1 here is raised to the lag I. Okay? I appears in the form of lags. So this comes along with the error terms. I'll just show you all something. I hope you all will be able to understand it. Yeah, I'm not sure if you all will, but let's see if it makes some sense at least. Okay? So what I've done here is I've generated a set of random numbers, okay, which are normally distributed, and I've given them a specific mean value and standard deviation. The choice was completely arbitrary. Okay? So I've generated these random numbers. Now this will keep changing every time I click on it. So I just saved one set of random numbers. Okay, so I've generated about 100 random numbers like this. Okay. Now what I've done is I'm looking at a particular difference equation or a particular AR1 process. Okay. So this process takes the form yt is equal to 0.9 yt minus 1 plus et. Okay. Just keep that in mind. Yt is equal to 0.9 yt minus 1 plus et. Here, these are the error terms. Okay. So I've used these random numbers which I've generated to generate my error terms, which have a specific mean value of 0. Okay? Since the mean value is 0 and I've given them a constant variance, they are basically white noise processes or white noise error terms. Okay, now let's just look at this. Now to generate the first value, okay, I've assumed that y0 is equal to 1 or y0 is equal to 1. That's the initial condition from which I'm starting. Then after that, for the second one, okay, here I'm taking y1 is equal to 0.9 y0 plus the error term. Okay, that's how I've taken it. You'll be able to see the equation here. Okay, these are my error terms and this is y0. E1 is y0. Okay, so I've generated this whole time series or this whole AR1 process this way. Are you all with me so far? You all are able to follow? Did you all understand what I've done at least in this Excel sheet?
Yes, ma'am.
Okay. So here in this part, okay, in this column, what I've just taken is 0.9 raised to the power 0. Okay, this column gives me time running from 0 to 100. So I've just taken the value of a1 or 0.9 raised to the power t. Okay, so this is that term. If you're looking at ab raised to the power t or a1 raised to the power t y0, okay, this is that a1t term. Okay. I think you all are a little tired, but I'll just show you this. We'll go through it again tomorrow. So hopefully you all will understand better. Okay. Now this is the graph that I've been able to generate using this. Okay. So now since I've assumed that a naught, okay, there's no a naught in my equation here. Okay, so a naught is basically taking a value of 0. My difference equation or AR1 process is simply yt is equal to 0.9 yt minus 1 plus et. Okay. So here the mean value or equilibrium value to which this series is trying to converge is 0. Okay. And you can see that there is convergence because b or the value of a1 that I've chosen is the absolute value is less than 1. Okay, so that's why there is convergence. Just go back to the difference equation part that we discussed. If the absolute value of the b term, okay, is less than 1, then you
Ma'am,
see convergence. Yeah.
can we say that series 2 is one of the components of how we depict series 1? The orange line is one of the components when we are depicting the blue line.
Yes. Yeah. Okay. This is because you're taking 0.9 raised to the power of time. Okay. Raised to the power t. So because of that, it will be part of this overall picture here that you see from the fluctuations part. Okay. So it is one component of it. But what you'll notice is this is dying down. Okay. Since the absolute value of a1 here is less than 1, okay, so you see convergence happening. Okay. In addition to that, we'll discuss some more features of this process tomorrow, but I hope you all understood at least one aspect from this. Okay. That's why we were assuming earlier that A1, modulus A1 or the absolute value of A1 is less than 1, so that that particular term vanishes. Okay. I'll share the notes for this so that you all can go through this before tomorrow's class, then we'll be able to discuss more.
Thank you, ma'am.
So I'll quickly take attendance. If you all have any doubts, any questions, you can just note it down, all right? And we'll discuss tomorrow. Yeah, I'm setting the default to you are present. Okay, so wherever people are absent, I'll just mark them absent. Okay, so Akash Singh,
Yes, ma'am.
Achal Jain, Ayush Bhushan,
Present, ma'am.
Adyasha, then Tejas Milind, Ali Asgar, Anjali Garg, Anmol Sen,
Present, ma'am.
Anmol,
Ma'am, present.
then Arismita Deka, Arismita, Avni, Avni Mishra, Ayushi, then Sarvesh,
Present, ma'am.
okay, Bhavya, Terry,
Present, ma'am.
sorry, then Diksha, Deepansha, Gaurav,
Present, ma'am.
then Gaurav Santosh, Himanshi,
Present, ma'am.
Jaideep,
Present, ma'am.
Ayushi, Ayushi K, Krishan Kant Shukla, Kriti,
Present, ma'am.
Mansi,
Present, ma'am.
Mansimran,
Present, ma'am.
Manvi,
Yes, ma'am.
Mihir,
Yes, ma'am. Present.
Muskan,
Present, ma'am.
then Namrata,
Present, ma'am.
Neil,
Present, ma'am.
Nikhil,
Present, ma'am.
Prasoon, then Pratik,
Present, ma'am.
Rachit,
Present, ma'am.
Rahul Ghosh,
Yes, ma'am.
Rahul Giri, Rahul Goswami, Rajaditya,
Yes, ma'am.
Rashi, then Rishav, Ruma, Sahaj,
Present, ma'am.
Samiksha,
Present, ma'am.
Sharanya, Shubham, Shubham Jain, Shubham Kumar,
Present, ma'am.
Ram Shankar Verma, Someshwar Ram Shankar Verma, Stuti, Then Thakur, sorry.
Ma'am, I'm present, Stuti.
Okay. Sanika,
Present, ma'am.
Vinaya, Mihir, you already answered, right?
Yes, ma'am. I think it's the wrong sheet.
Repetition. Okay. Any names that are missing in the other sheet? Sushri, Sucharita.
Ma'am, it's an old sheet. Lot of students are left since then.
Okay, so none of these people are here. Deepak
No,
Kumar.
ma'am, there are there, but this is, I guess, wrong sheet.
Okay.
The previous one was correct.
Okay, they are no longer part of your class. Hi. Oh, sorry. Ayush Sharma, Alicia, Anam, Vidhi, Jiten, Amisha, then Anant, Prabhat, Anish, Anish Ajay, Anjali Sethi,
Present, ma'am.
Arshada,
Present, ma'am.
Barkha, Bhavya, then Saloni, Tetra, Devam Pandey,
Present, ma'am.
then Diksha, Gorja,
Present, ma'am.
then Gayatri,
Present, ma'am.
Mittal, Govind, Savan,
Present, ma'am.
then Himanshi,
Present, ma'am.
then Indu, Ishita,
Present, ma'am.
sorry, Kanika, then Kartik Mittal, Astro, then Lakshay Singhal,
Present, ma'am.
Mahi,
Present, ma'am.
Mansi Gupta, then Matangi, Megha,
Present, ma'am.
Nancy, Neha,
Present, ma'am.
Pratishtha,
Present, ma'am.
Rohan, Rohit,
Present, ma'am. Ma'am,
uh,
Bhavya Patel has raised his hands. I guess he's present if you have marked him absent. Bhavya Patel.
just give me a minute. Let me finish this and then I'll look into that.
Okay, ma'am.
Yes, Samidha,
Present, ma'am.
Shivangi, then Simran,
Present, ma'am.
Srishti, Tanu, Tarang, Kalyani, Twinkle, Vaishnavi, Vanshika, Vibhor,
Present, ma'am.
Vidushi,
Ma'am, present.
Vibhor is present,
Yes, ma'am.
Vidushi, Yash Mehra, Just give me a minute. Yeah, who raised their hand?
Ma'am, it was me, Bhavya Patel. I tried to switch on my mic, but it wasn't working at that time. I wait for you to complete them.
Okay, which are you in IBEF for the other?
Yes, ma'am. IBF 2011 is my roll number.
The roll numbers are not.
It's the 10, serial number 10.
Wait.
11, sorry. 10th or 9th, sorry, my bad. 10th is 9th.
Okay, Bhavya.
Yes, ma'am. Bhavya.
Your name is Bhavya, right? Or
It's Bhavya.
Bhavya. Okay, sorry. Any other corrections? All fine. All right. So we'll meet in tomorrow's class. I'll try and share today's set of notes with you all, so you all can go through it, see if you all have any doubts. Yes, then we'll discuss more in tomorrow's class. Right. Thank you for your time. We'll meet tomorrow.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.